taxi accident when he was coming back from Oslo with his Nobel Prize. And so they have talks. They asked me to talk about algebraic geometry. Other people talked about his contributions to differential geometry analysis, game theory, etc. He was an amazing mathematician. He didn't have a specialty in mathematics. He just learned about some famous problem and just start thinking, start asking experts questions. The beginning of the questions were very stupid, but very naive. But after a few weeks, he would get the hang of it and start becoming a specialist. And he solved so many of great problems. But his contributions to algebraic geometry, that was his last active period. He was in his 30s before he stopped doing mathematics due to his illness. So I want to talk about two main contributions. They're more than theorems, more than great theorems. They're questions and conjectures, new ideas which open to big lines of research. That's what I want to talk about. Both are related to resolution singularity. So the first part of the talk, I'll try to explain from scratch what resolution singularity is, and in particular Hironaka's proof of resolution characteristic 0. I'm talking on Monday in Oaxaca, and a lot of the same people will be there, so I decided today to give a more general talk, and in Oaxaca it'll be more advanced, and I have to do more with my own work on resolution characteristic P and so forth. Okay, so let me start from scratch. So our basic object is an affine algebraic variety. So I start with some ground field K. So for most of the time you can think that K is equal to C. And this talk I'll mostly be in characteristic 0. An affine algebraic variety is a subset of the Euclidean space defined by finitely many polynomial equations. Let's see, where's the... Oh, how do you cannot erase here? Or
you can erase it.
But with one of these?
Yes.
Yeah, okay. So it's a set of zeros of finitely many polynomial equations. Equal to 0, where the fi's are polynomials and invariables. Let me put some examples of singular algebraic varieties on the board, examples we'll use later. For example, the nodal curve. Like this. Non-singular quadratic cone. So this is z squared minus x squared minus y squared equals 0. And this is sometimes called, this is probably the simplest surface singularity. Sometimes this is called the A1 singularity, but we'll look at slightly more general ones, which are called AN. I don't really know how to draw them. I just know how to write down the equation. X squared minus 0. So I guess it looks something like this. It looks similar but thinner. Yeah, I don't really know how to draw this well, but okay. So most points on an algebraic variety are singular, and not singular. I mean, locally the variety looks like a piece of the Euclidean space, but there are some exceptional points like the origin here and here and here, which are called singularities. Algebraically, they're detected by vanishing of partial derivatives. So in general, if x is given by a single equation, its singular locus is given by vanishing of all the partial derivatives of this equation. So it's And in general, maybe I should mention mention the word irreducible. All the varieties are, because we'll need it later. All the varieties I have here are irreducible. So a topological space X is called irreducible if you cannot write X in a non-trivial way as a union of two closed sets. So whenever X is union of two closed sets, this implies that X is equal to X1 or X2. So of course, in the classical Euclidean topology, this is not a very interesting notion. The only irreducible sets are points. But in the Zariski topology, in which my closed sets are subvarieties, this notion makes sense. So I'll often assume that my varieties are irreducible without saying it explicitly. So maybe I won't write it down, I'll just say it in words. So if you have a irreducible variety described by some prime ideal, then the singular locus is given by the vanishing of appropriate minors of the Jacobian matrix. The minors R by R, where R is the codimension. So for example, in all these examples, you detect a singularity by the fact that my equations have no linear terms in the origin. So my main interest in mathematics is in studying singularities is to get rid of them by certain permissible transformations. So let me by rational transformations, which are or blowing up. So let me explain what they are. So of course we have a natural notion of morphism between algebraic varieties. They're just all they are is polynomial maps. So let pi be a morphism. So I say that pi is birational. If there exist proper subvarieties y of x and y prime of x prime. By the way, I forgot to say here that in particular singular locus is a subvariety. It's defined by imposing some extra equations. So if there exist such subvarieties, that away from them I have an isomorphism. And we'll do many examples of this in a minute. So let me define resolution of singularities. A resolution of singularities of X is a birational proper morphism such that X prime is non-singular. Okay, so proper means, since we're working over C or over R, proper means usual proper with respect to classical topology. Preimage of compact is compact. In general, for example, over characteristic P, it's quite difficult to define what we mean by proper, but it's not trivial to define, but I won't do it today. And obviously, so I'm going to talk about the problem of resolution of singularities. Obviously, if we didn't say this word proper, the problem would be completely trivial, right? Because we could just take x prime equal x minus y. But that wouldn't be proper. Okay, so let's give some examples. So for example, for the nodal curve, intuitively it's kind of obvious what to do, right? We just take apart. So my birational proper morphism consists in just taking apart the two branches. And so in general, birational morphism means that we usually just throw out the singular locus, but then we have to glue something else in its place to make the thing proper, and so the whole thing is non-singular. So in this case, in the case of a nodal curve, intuitively it's clear we should throw out the origin, the singular locus, and just glue 2 points in its place. But of course we want to do everything algebraically with formula. So usually what what is done, for example, what Hironaka did in his famous proof was, usually we transform the ambient non-singular space and then see what happens to the singular subvariety. So let me talk about blowing ups. So blowing up the plane at the origin, that's the simplest one. Oh, and I forgot to mention another thing, another terminology that I'm going to use is that usually this y is usually called the center of blowing up. And the y prime is usually called the exceptional set or exceptional divisor. Okay, so to blow up the plane at the origin, what we do is it means that the center of blowing up is going to be the origin. We're going to throw the origin and glue something else in its place. So let's consider what are we going to glue in its place. Let's consider totality of straight lines passing through the origin. They form a P1. So let's remove the point and glue in a P1. If ever the reals that P1 is just a circle, and so we remove the origin, we glue in a P1, and now these lines upstairs, this P1 sort of parameterizes the slope of the line, so now these lines become disjoint upstairs. But so this is isomorphism away from the center of blowing up and away from the exceptional divisor. And we want to be able to calculate everything with coordinates. So if my original coordinates were x and y, upstairs my variety is no longer affine. It's glued together from two affine pieces, from two planes. and this notation just encodes coordinate change, how they're glued together and how what's the transformation is to the variety downstairs. And this allows us to calculate. So you see, in each coordinate chart, x equals 0 is the equation of the exceptional divisor, the local equation of the exceptional divisor, and this is the coordinate along the exceptional divisor. So in particular, if you think of the exceptional divisor itself, that's why you get P1. You get y over x on one chart and x over y on the other. Okay, so let's do some calculations, which we'll use later. So for example, what I just drew there, we can do it. So let's call this these variables x prime, y prime. We know the transformation law, namely we know that x is x prime and y is x prime, y prime. So we can write y squared minus x cubed is y prime x prime squared minus 1 minus x prime. Minus x prime squared minus x prime cube. So now this new variety became reducible, right? We detect reducibility by the fact that the polynomial is reducible. And this is normal because I'm doing blowing up of a plane, so I want to see what, this is my nodal curve here, so I'm computing the full preimage of this nodal curve, so it's normal it should be reducible because the full preimage contains the entire exceptional divisor. The local equation of the exceptional divisor is x prime, and that's why this polynomial is divisible by a certain power of x prime. So this is x prime squared, is y prime squared minus 1. So it's a union of the exceptional divisor of the parabola, just like we see on the picture. And this parabola, so the full preimage of my curve is not birational to the original curve, but if we remove the exceptional divisor, if we factor out x prime, then it does become birational. So in this part, which is birational, is called the strict transform of the original curve. We can do the same thing in higher dimensions. We can blow up a Euclidean space at the origin. It looks very similar. By the way, over the reals, this is just a very bad picture of a Möbius band, right? Because we have a S1, P1 is the same as S1, and we have one line which goes around and comes back to itself. So We can blow up Euclidean space at the origin. It looks very similar. I take the Euclidean space. I look at the totality of lines which pass through the origin. Now this time they're parameterized by Pn minus 1. So now the exceptional divisor is going to be Pn minus 1. N minus 1 dimensional projective space. And again, the lines become disjoint upstairs. So the picture looks very similar. This is the total space of a line bundle of Chern class minus 1. If you collapse the zero section, you get an Euclidean n space. And again, I'm interested in calculating things with equations. So here, if the downstairs I have an n-dimensional polynomial ring, upstairs now I have n coordinate charts, and the coordinate chart number I looks like this. xi plus 1, xi, x n over xi. So again, we have, this is the local equation of the exceptional divisor, and the remaining coordinates are coordinates along the projective space. Okay. And again, we can do, this is still not the most general blowing up used in Hironaka's proof of resolution of singularities, but it's very, very close. The most general one, so once you understand this picture, now think about what we can also do is we can just multiply everything with another Euclidean space. Just take a direct product of everything with the Euclidean space. So this will become blowing up of, well, I should not modify equations on the board. So this will become, we can blow up Kn plus L with center, or along, or with center, center KL. So just multiply everything by Euclidean space. That would mean, so now, that would just mean there will be a bunch of extra coordinates with which nothing will be happening. And now the new exceptional divisor will be a trivial vibration over KL by Pn minus 1s. And this is the most general blowing up that's used by Hironaka. So let me also, well, let me calculate these two examples because we'll need this later. I started at minus 20. I mean 22. Okay. Okay. So let's calculate these two examples. Calculation is very similar. It's, as you see, it's very straightforward. So for the quadratic cone, again, it's kind of obvious what's going to happen. We're going to replace this point by a conic. You can imagine what's going to happen, but let's do it. So, okay. Let's just do one of the coordinate charts. So upstairs, so let's say k y over x, z over x. So I blow up a point. Again, this is going to be x prime, y prime, z prime. I make the substitution. Y prime squared, x prime squared. So again, we see the same thing. The equation becomes reducible because it's the full preimage of my right. It contains the entire exceptional divisor. Local equation of the exceptional divisor is x prime. So I factor it out and I obtain a strict transform, which is yeah, I guess well, never mind. It's a conic. So is it? Right. So you might think, I guess you might think this is a hyperbola, but actually it's a hyperbolic cylinder because there's one variable. There's also the x prime variable, on which this doesn't depend. So I guess yeah, anyway. And for the next one, this is more general. Let me use a better equation. I mean, this equation is, let me. But anyway, the point is that So I have the exceptional divisor of the total blowing up, but so exceptional divisor now has two meanings. I have the exceptional divisor of the whole blowing up, but I'm interested to what happens on the strict transform of the variety, and that's a conic. If we did all the projective charts, we would just get a smooth rational curve upstairs. So here the exceptional divisor is irreducible and consists of a single smooth rational curve. Let me change coordinates here. Let me talk about x squared plus y squared is the same as xy in different coordinates. So let me look at this. And let's do exactly the same calculation, but this time let me look at, there's one coordinate chart which happens to be more interesting than others. So let me look at this one, x over z, y over z, and do exactly the same type of substitution. So let me call this x prime, y prime, z prime. So we get z prime to the power n plus 1 minus x prime, z prime, y prime, z prime. So again, it's reducible. So you see, this time we didn't resolve the singularity in a single step, but we get a singularity which is better than before. So this one is called the AN singularity. And this one here, the strict transform, is AN minus 2. So we improve the situation, but I am interested in what shape the exceptional divisor has. So you see here, z prime equals 0 is the local equation of the exceptional divisor. Therefore, the exceptional divisor consists of two lines. Well, I mean, assuming n is greater than 1. So here, z prime if z prime is equal to 0, then so is one of. So here the exceptional divisor consists of two lines. Z prime equals x prime equals 0, and z prime equals y prime equals 0. So the exceptional divisor on the blown up surface looks like this, and the singularity is right in the middle. It's on the intersection of the 2 points. So we iterate the procedure, right? So clearly after about n over 2 repetitions, we'll resolve singularity. And what turns out, so for example, the next iteration, it's going to look like this. So these are these are strict transforms of the two old exceptional divisors. These are the two new ones, and the singularity here will be AN minus 4, and so on. So after suitable number of iterations, we'll obtain resolution of singularities. So let me call this variety X for now. So we'll obtain resolution of singularities of X. And I'm always interested in the preimage of the singular locus. In this case, the singular locus is the origin, and it looks like a union of n smooth rational curves. Okay, so it's reducible. It has exactly n irreducible components, and it just looks like a bamboo, a bunch of lines. Okay, so in the early 1960s, Hironaka proved that any variety over a field of characteristic 0 admits a resolution of singularity. That was a very big deal. It was a big breakthrough. He got his Fields Medal for this. And Nash was also very interested in it. By that time, Nash already had been to several psychiatric hospitals, but he was taking medicine. There was about a year or two where he could still work. And that's when he worked on algebraic geometry. So Nash was very excited about Hironaka's proof of resolution of singularities. I think the official year is 1964. If case of characteristic 0, every variety admits a resolution of singularities. In fact, his theorem is a little bit stronger than that. I won't write it down, but there's something you can say. First of all, it's an isomorphism precisely outside the singular locus. It doesn't modify non-singular points. That's one aspect of it. And another aspect of it, that it's obtained by blowing up, which are all locally of this kind. It's obtained by blowing up the ambient Euclidean space along a non-singular subvariety, and then contained it in the singular space X, and then seeing what happens to the strict transform. So if you believe this, if you believe everything I said until now, it's immediately obvious that this proof must have a certain inherent complexity in this proof, because, and in fact, the original proof was about 200 pages. The modern simplified proofs, as far as I know, it has come down maybe to 50 pages or so, but nobody knows a really simple proof of this. And so why it's obvious that there's a certain complexity involved, right? Because you see that, in my examples are very simple because I always had a single isolated singularity. But in general, a singular locus can be a complicated subvariety, which itself may have singularities. So a priori we have a hierarchy of singularities, a certain tower of subvariates. And if we insist that we only modify singular points and only by blowing up along non-singular subvarieties, then at least the least you should do, you should in the process resolve the singularities of this and blow up this singular, and then you get a similar problem on each level, right? So it's obvious from what I said that there must be a certain hierarchy of singularities, and you sort of you start with the worst, resolve the worst one first. And this is indeed how Hironaka's proof goes, except the hierarchy is much more subtle than just taking a singular locus at each time. There's much more delicate numerical invariance. So apparently Nash was very excited about this, and as far as I know, he didn't write this down, but Hironaka reports that in a private conversation, Nash suggests a very beautiful, canonical, simple algorithm, conjectural algorithm to resolve singularities. But unfortunately, well, let me tell you what Nash's suggestion was. It's called Nash blowing up. Maybe I should say before I do this. So the usual blowing up, sort of the most general, so more general than the ones I described here, is the following: that we can take a subvariety of X defined by certain equations, and we can consider the map phi from X away from the subvariety. So this is the zero set of some equations. Map to so if my variety is defined by S equations, I map X minus Y to S minus 1 dimensional projective space using these equations, right? So each point goes to G1 of Xi to the S tuple G1 X. And this makes sense precisely because I'm away from this common set of zeros. So this is a well-defined point in the projective space because I'm away from the common set of zeros of these polynomials. And then what we can do is we can consider the graph of phi in X times the projective space, and take the Zariski closure, take the closure, and project on the first coordinate. And we get something which is birational, proper, projective. So in all my examples, so for example, blowing up the plane at a point, we just take the GIs to be the coordinates X and Y. Similarly, blowing up a Euclidean space at a point, just take look at the variety defined by X1 to extend it and do this procedure. So what Nash suggested was the following. Let's consider, so let U denote the non-singular locus of X. That's the regular locus of X. And let's consider the Gauss map to the Grassmannian. So let's say, let me change notation. Okay, so let's say the dimension of X is, let's say M. So, and let's say that X is embedded into, say X is affine embedded into n-dimensional Euclidean space. So let's consider the Gauss map, which goes from the non-singular locus to the Grassmannian of all M planes in N space. Okay, now I'll denote this Grassmannian by G. Okay, so what the Gauss map does is just takes any non-singular point and maps it to its tangent space. But I view the tangent space as an element of the Grassmannian. That's the Gauss map. And then Nash does exactly the same procedure. Consider the graph of this and take the closure. And you obviously get something birational and proper. So let's consider, let me denote the Gauss map by phi. So we consider the graph of phi inside x times the Grassmannian, and take the closure and project on the first coordinate. So what Nash blowing up does, it obviously leaves, it's obviously an isomorphism of the non-singular points by construction. So what it does is it does nothing to non-singular points, but every singular point is replaced by all the possible limits of tangent spaces to non-singular points converging to it. So for example, so again, maybe I shouldn't have raised this, our good old friend, the nodal curve. You see that the non-singular points are not going to get modified, but at the singular point there are two possible limits of tangent spaces, of tangent lines converging to it. And therefore, again, Nash blowing up does the same thing. It just separates the two branches because I have two different points in the Grassmannian, two different limits of tangents. The same, so obviously this resolves singularities for if you have any curve with any number of branches as long as they have distinct tangents. So if non-singular branches with distinct tangents, the result will be the same. And Nash asked Hironaka the following question. So now this is much simpler than Hironaka's algorithm, and it's completely canonical. The way I define it is not completely obvious it's canonical, because apparently it might depend on the embedding, but in fact it doesn't. It has certain universal mapping properties. So it's not hard to see that this is canonical. And so the obvious question kind of presents itself: iterate this procedure. Do we get resolution of singularities? That was Nash's question to Hironaka. So we iterate Nash blowing up. So we get a completely canonical sequence of birational proper or projective maps. So let me call them, for example, mu1, mu2, and so on until mu_i. And so Nash's question was, does xi become non-singular? Non-singular for I sufficiently large. And this is very beautiful. If this worked, this would be a very beautiful proof of resolution of singularities, but unfortunately nobody knows. Nobody knows if it works. So, sorry?
It's open, the question?
Completely open, yeah, completely open. Yeah, I'll tell you what is known. Very little is known. So, no. It's another Nash problem, which I may or may not have time to talk about. But yeah, this is. I'll tell you what is known. The list is very short, so it won't take a long time. So. So what is there is a result of Augusto Nobile from I think around 1970. Nobile is an Argentinian mathematician working in the United States. I think it's around 1970. It says that Nash blowing up is an isomorphism. If and only if x is non-singular. Well, this is obviously good news, right? Because if this was not true, then of course there would be no hope. One direction is obvious. If x is non-singular, of course, Nash blowing up is an isomorphism. But the converse is not obvious. It's not a trivial theorem. So if Nash blowing up is an isomorphism, that only happens when x was non-singular to begin with. This is obviously good news, because otherwise there would be no hope, right? By the way, this is false in characteristic P. Let me give you a counterexample in characteristic P. So if x is a curve, plane curve, defined in the plane, so yp y to the p minus xq equals 0 repeats the characteristic. You see that, maybe I'll say something more for the experts. So I explain what it means to blow up along an ideal, which may or may not define a non-singular subvariety, which just defines something. So if X happens to, this is more for experts in algebraic geometry, if X happens to be a complete intersection variety, then Nash blowing up is the same as blowing up the Jacobian ideal that I was talking about earlier, okay? So that's true in all characteristics. So here, okay, let's compute the Jacobian ideal, right? The Jacobian ideal is just Q, so let's say P doesn't divide Q. So the point is that one of the partial derivative vanishes, identically 0. Therefore, the Jacobian ideal is principal. And it's kind of, I didn't say this, but it's kind of obvious from definition. If you blow up along a principal ideal, you get an isomorphism, you get nothing new, because you map to a zero-dimensional projective space. Your map goes to a zero-dimensional projective space. Okay, so, and then an immediate corollary of this, or almost immediate, is that the answer is yes. So answer to Nash affirmative is yes if, in characteristic 0, if dimension is 1. For curves, it does work. Why? Because you see, for curves, we already know that there are many ways to resolve singularities. One of them is normalization. It's passing through integral closure of the coordinate ring. And the normalization is finite over the curve. So for curves, we know that there's only a finite distance, so to speak, from the normalization is a finite module over the original curve. And so if you know that something changes at each step, and the whole way is finite, you know that you'll get there. That's the you cannot have an infinite ascending sequence of submodules of a finite module. Okay, so, but that's about it. I mean, there's very little else. There is a variation of this, so you can iterate either Nash blowing up or so let me refer to this as n, but we can also do nn, which is Nash followed by normalization. Again, I don't have time to go into details. Normalization is the process. This was defined in the 1940s only after algebraic geometry was algebraized by Zariski, because it's a very natural algebraic transformation. It's not so easy to say what it means geometrically, but it consists of changing the notion of regular functions, adjoining all those functions which are integral over the original ring. So analytically, you might think of it, it's adjoining all the meromorphic functions which are locally bounded. Okay, that's one way of thinking about it. But anyway, it's a canonical process. It's a finite map. So you can so my PhD thesis was that also yes if dimension is 2, but only for Nash normalization. So it's still completely open for Nash itself. There is this is a long proof. This is maybe 160 pages. So it's again no easy proof of this is known. There was a earlier theorem by a person called Rebassou, also a PhD thesis, where he did a very special type of toric surfaces. So for Nash blowing up without normalization, but for a very special type of surfaces of this form, hypersurface, also quite a difficult proof, highly non-trivial, and pretty much that's about it. So it's not known for surfaces without normalization. Let me finish this part of my talk by telling you an open problem, and also mentioning some partial results of my Mexican PhD student, Daniel Duarte. So let me start with an open problem, okay? So the question was to at least answer Nash's question for toric varieties. Right? Toric varieties came up a few times in this conference. So there are varieties which contain an algebraic torus, and in which the algebraic torus acts with itself being an open dense orbit. And and as I mentioned, they're a great source of examples because they're basically combinatorial objects. So in principle, every statement can be translated into combinatorics, and therefore, so one thing, we could translate statements into combinatorics and hope to solve the combinatorial problem. Sometimes we can, sometimes we can't. But also, I think, as Ernesto mentioned, it goes the other way around. Sometimes the standard results from algebraic geometry, like Hard-Lefschetz theorem, point-carrier duality, produce highly non-trivial combinatorial facts about polytopes. So I'll tell you a combinatorial problem. Let me work on the plane. You can do n dimension. So let's consider the plane. Let's consider a semigroup inside the integer lattice. So I'll call my semigroup phi. Let's say it's generated by finitely many vectors. So this is all a semigroup living in Z2. Okay, let me draw them. So it's just all the positive integer combination of this gamma 1, these vectors with integer coefficients. And so on. By the way, I'm talking about not necessarily normal toric varieties. So the way I think of the toric variety is that let t be the torus variables, t1, t2, and let's just consider t to the gamma 1, t to the gamma s. So this is multi-index notation. It's gamma 1 has two coordinates, so it's t1 to a certain power and t2 times t2 to a certain power. And just consider the ring generated by these. Okay, so and this is the coordinate ring of my toric varieties. And here you see immediately the map of the torus, which goes this way. But it need not be normal. I'm not asking for it to be normal. Okay, and let's consider the following game, or the following transformation. So let me fix an irrational number, some kind of irrational slope, alpha. It's an r minus q, and let me consider the linear functional L of xy, which is just alpha x plus y. Okay, so I think this is defining a certain slope, irrational slope on the plane, and therefore, because alpha is irrational, this gives me total ordering among the gamma i's according to the value of alpha. So let's order them in such a way that L of gamma 1 is strictly less than L of gamma 2, and so on. So my transformation is going to be the following. I start with phi, and I replace phi by the following. So phi gets replaced by phi prime. Phi prime consists of gamma 1, gamma 2, the two smallest ones, and then all the differences, gamma I minus gamma 1 and gamma j minus gamma 2. And there is a non-degeneracy condition which is not very important, which you don't have to think too much about, but it's usually automatic. But I want some determinants not to vanish, but usually they don't vanish anyway. Okay, so you see, I start with one semigroup and I create a new one, which looks like it has a lot more elements. It looks almost twice the generators as before. Of course, nobody says that they're minimal generators, and even in the beginning, I didn't necessarily say that they're minimal generators. They might be expressible, some in terms of the others. Well, what does it mean to win? What does it mean to resolve singularities? Well, people who know toric varieties, I think this also came up before, people know very well what it means for toric surface to be non-singular. It just means that my semigroup is, up to automorphism is just a standard unit vectors, right? Or in other words, my semigroup has two generators. I forgot to say that, as usual, I'm assuming that these generate Z2 as a group. That's the usual assumption. Okay, so we create this sequence of semigroups. Let's say phi prime, so until phi I. So again, the question is phi I generated by two elements for some I? Of course, once it's generated by two elements, then everything becomes an isomorphism. Nash blowing up becomes an isomorphism. So this is very strange. It seems like the reason I stated for an irrational slope, it's easy to state a similar thing for rational slope. You have to change a few things a little bit, but for rational slope, it's known. That's one of the results of Daniel Duarte and his thesis. That's also independently that was proved by Tessier and Pedro González Pérez. They proved it in all dimensions, but I think there's not much difference. Actually, I told Daniel to stop working on this because there was competition, and there's not much difference. He could have done n dimensions also. but for irrational slope, this remains open. And if anybody can solve this, you will have proved that the answer is affirmative in dimension 2 for toric surfaces. Okay, so I still have a little bit of time, I guess not that much, but I'll say a few things about the arc spaces as much as I have time for. So this was probably Nash's last work before he sort of stopped doing mathematics due to his illness, and it's also related to resolution of singularity. It's a statement about existence of bijection between two finite sets. One finite set is the number of irreducible components in a resolution of singularity, roughly, and the other one is the number of irreducible components in Nash's space of arcs, which is an infinite dimensional algebraic variety. So all of this, Nash wrote this in a paper. I have this, I mean, if you can look at this later, this is a bit of a bibliographical rarity. He sent this paper to one of the best journals, I think maybe Invenciones or Annals of Mathematics, and Hironaka was an editor at the time. And so you could see the language is very strange, so you could see that this person has some problems. But the mathematics is actually very solid. If you read the mathematics carefully, there's nothing crazy about the mathematics. But because it's written in such a strange language, the editors didn't know what to do with it and decided not to publish it, but they kept the manuscript. So this is not quite the original manuscript, but it's the original copy of the original manuscript. So you can look at it, it's typewritten. And so some privileged people kept a copy, and it had a tremendous influence on many people started to work on this Nash problem, and it was finally published about 30 years later. So I mean, I think they made a mistake by not publishing it. So let me just say a few words as much as I have time for. So Nash's, it's a very, very beautiful object, Nash's space of arcs. So it's the following. I start with X and algebraic variety. Mostly I'll take X to be an affine algebraic variety because my interest is local. And I consider the following object. So what's an arc? An arc is a morphism from this object to X. So if you don't know specs, that's okay. I mean, it looks scary, but so you should think of it as a test curve. It's a parametrized test curve. Okay, so formally this is a topological space which only has 2 points, the special point and the generic point. And I'll denote the generic point by eta and the special point by 0, the origin. So think of, if you are a complex analyst, think of it as a kind of small test disk, or a small germ of a unit disk or something like that. Okay. But anyway, we'll see in a minute that these are actually very parametrized curves. Formal curves are extremely concrete objects. So for example, let X be the Euclidean space. So the simplest example is the Euclidean space. So if X is the Euclidean space Kn, so what does it mean to specify such a parameterized formal curve? All it means is just writing down n formal power series. That's all it is. So a typical formal curve looks like this: is A10 plus A11t plus A12 t squared and so on. And then you do this for all the variables. And so on. I'm mostly interested in singular, in the case where X is singular, and actually I'm interested in those curves which pass through the singular locus. Actually, the closed point lands on the singular locus. That's the main Nash space of arcs. So let me call this H. It's the set of arcs x such that the special point lands on the singular locus. Okay. So I mentioned, I'm not sure I said explicitly, in Zariski topology, usual algebraic varieties are usually Noetherian topological spaces, and therefore every algebraic variety can be written uniquely as a finite union of irreducible components, finite union of irreducible subvarieties. But this one, so you see from this example, it's more or less clear. It's natural to think of it as an algebraic variety, but an infinite dimensional one. Right, the infinite many coordinates. Okay, so therefore it's not obvious this. I mean, we can talk about the irreducible components, but it's not obvious that there's finitely many of them. But Nash, that's one of the things that Nash proved in his preprint. So let me quickly describe what they are. So let's take a resolution of singularities. And let's, for simplicity, I don't have to do this, but just for simplicity of exposition, let's assume that X itself has only an isolated singularity. So let's take C. And let's look at the resolution of singularities. Let's consider the exceptional divisor. Let's consider its decomposition into irreducible components. So, for example, in the case of n singularity, which is pretty much the only one I calculated, the number of components was n. Okay, and now let's observe the following. Actually, this is true for any. So now let's consider an arc. So let's consider an arc which maps to x. So I calculated a few examples where we looked at strict transform of curves. So for example, the nodal curve had two branches at the origin. Therefore, the strict transform upstairs intersected the exceptional divisor in two places. But these ones you should think of as being unibranch. So there is actually a unique point upstairs where it's strict. So the notion of strict transform can be generalized easily to this and calculated in the same way. So it turns out that, so if this is phi, as long as my curve, as long as it's not the trivial curve which maps everything to the singular point, there is a unique way of lifting it to the resolution by strict transform, and it will land on one of those. So the special point would end on one of those exceptional divisors. Okay, and so this allows us to write down a partition of Nash's space of arcs. So let Ni to be the subset of H or subspace, subvariety, such so all those arcs phi, such that phi prime of 0 lands on EI. Okay, and so what Nash proved is actually not hard to prove. It's proved in the preprint. Two things. First of all, that each Ni is irreducible. There is a natural, I forgot to mention this, there is a natural notion of Zariski topology on this. This is simply, well, it's, if you like, it's inherited from the Zariski topology arc space of the Euclidean space, but all it is so a closed set is a subvariety defined by finitely many equations and finitely many variables. Okay, so there's a natural notion of Zariski topology. Just whatever you can do with finitely, although the total number of variables is infinite, you can talk about subsets defined by finitely many equations and polynomials and finitely many variables. And therefore, I can talk about irreducible. And the second thing is that the whole space of arcs is the union of the closures of these. And so, in particular, it follows immediately that maybe I should say something about the proof. This is almost obvious from what I said before, right? Every curve has to land somewhere on some EI. That's all there is to it. But this is less obvious, but it's also not hard. The idea of proof is the following. So let me write down so these are the EIs. So the EI is non-singular at its generic point. And the whole variety is non-singular. So we have a non-singular subvariety of a non-singular variety. And so what one shows is that away from some special points, from some singular points, my Ni has a structure of a fibration by Euclidean spaces over something non-singular. That's kind of obvious that that's irreducible. That's basically the proof. So now it's immediately obvious from this that, okay, corollary, H has finitely many irreducible components. Why? Because the irreducible components are among these. But they don't have to be exactly this. It may be a subset. Why? Because so it might happen. So this is a remark. A priori, it may happen that Ni is contained, or some of these guys might be contained in closure of others, and those for which it happens are not irreducible components, right? So we only know that the set of irreducible components is a subset of this, and basically the Nash problem, roughly speaking, it asks to identify the irreducible components of it. So to be precise, I don't have much time, so let me just say very quickly. Of course, the resolution of singularities so you might naively conjecture. Let's just conjecture that this is the set of irreducible components, right? But this is obviously false. It can't possibly be true because, in general, resolution of singularities is far from unique. In particular, once singularity is non-singular, you could blow up a non-singular point, and you get an extra component. So this number is not constant, right? So this naive conjecture could not possibly be true. In the case of surfaces in dimension 2, there is a kind of natural canonical choice. There is such a thing as the minimal resolution, through which all the others factor. So there is a natural candidate for being the exact set of irreducible components. And for surfaces, this is true. This was proved recently by Javier Fernandez de Bobadilla and by Epe. This is a very, very brilliant proof, very non-algebraic, which kind of angered the experts. The experts didn't want to accept the proof for at least a year, but it's a very brilliant idea. And I don't have time for much more. There was a lot of, but just to give you an idea, only less than a year before their proof came out, with a student of mine, Camille Plenat, we proved the case of E6 singularity, which is one of the simplest surface singularities. So it was not known even for simplest classes of surface singularities. And then for higher dimensions, well, I don't have time for much more, but there is a notion of so-called essential components of the exceptional divisor. This notion is so if I look at two different resolutions, there is a rational map going from one to the other, and the rational map is always defined at the generic point of a divisor. So it makes sense to talk about the image, even if the map is not well defined everywhere. It makes sense to talk about the image of this divisor on the other resolution. And the essential ones are those that appear on all the resolutions. So this is well defined, and so this was the Nash conjecture in higher dimensions. Nash was very careful not to say that he conjectures it. He called it a question, and this turned out to be false. There was a counterexample in 2002 by Ishii and Kolar, and then after the affirmative proof in dimension 2, Tommaso de Fernex gave two examples in 3 dimensions. And then there was another very beautiful. So now there is Kolar defined something, a smaller set called very essential components. And it's kind of obvious that this is the best we can do, but not much is known. And maybe the last thing I'll say today about, after all these counterexamples were established, Kolar and Johnson wrote another beautiful paper with more counterexamples. And so for instance, it turned out that, x squared plus y squared plus z squared plus w to the 5. That's a counterexample to the Nash problem in 3 dimensions. And my students, Camille Plenat, my former student Camille Plenat, was very sad because she went up to to the power of 4. And she observed that it was not a counterizample. So if it's just 1 power. And so finally, the very last thing I'll say today, this is a special case of the following: x squared plus y squared plus z squared plus g in a whole bunch of variables. So what Kohler-Johnson show is that let's assume that the multiplicity of g is greater than or equal to 4. And what they show is that the answer to the Nash problem is affirmative if and only if g is a complete square. So this makes me think that, not everybody agrees with this statement, but it makes me think that it's more rare for Nash problem to be true than to be false. I mean, it's more special to be a complete square than not to be a complete square. Okay, so actually, okay, if you like, you can, my plan was to calculate the AN case explicitly, and you can all do that and observe that there are indeed n irreducible components. You can identify what they are, so one can check. The AN case was done by Nash in the same preprint. So, okay, so I think it's a good place to stop.
So, I mean, it's a silly question maybe. If in the definition of the Nash blow-up, instead of a tangent linear space, you take a tangent space up to some degree.
Yeah, that's excellent. Yeah.
I mean, what do you get then?
That's a very good question. It's known. It's not so trivial to define because it has been defined fairly recently. It's not so trivial to define. It's of course a very natural idea. The reason it's not so trivial to define is that there's no analog of Grassmannian, which is compact. I mean, my definition works because Grassmannian is a projective variety. There's no analog here, but you can still do it. You can define it using Hilbert's scheme of points, and so Hilbert's schemes are compact. So this was defined by Yasuda. Not that long ago, maybe I would say 10, 15 years ago, about 10 years ago, I think. Then my former student Daniel Duarte gave his own definition. Actually, he did manage to use Grassmannians. And so there is a very natural conjecture, which is true for curves. So if you do this and apply this to curves, it's not that hard to see that for n sufficiently large, you resolve singularities. So you can ask the same thing in all dimensions. There is a conjectural counterexample, which is A3 singularity. So a conjectural counterexample is this, right? It's Z4 minus XY equals 0. That's the A3 singularity. And Daniel Duarte did an enormous amount of computer calculation both for this problem and for this one. So this one is just unreal. Nobody understands what's going on with double and double and double number of generics, and suddenly it comes down to 2. Nobody knows why. There's no general proof. And for this one, he got up to, I think, order 100 or so. And this is a toric variety, so he can calculate as toric varieties. And so he knows, conjecture, he knows exactly what's going on. He knows exactly why it's singular, and what the conjecture is. There is a column in the fan, or in an angle in the fan, which is singular, but it's only conjecture. He cannot prove. He sees it up to degree 100, but no proof. So probably this is a counterexample, but we can't prove it.
Any other question? Well, on behalf of all the participants, let me thank again the organizers for this Congress.
So it was